We have seen the PMOS common source amplifier with constant VGS biasing. Now we'll look at other ways of biasing a PMOS transistor, analogous to what we did with the NMOS transistor at a given current instead of at a given VGS. Okay. And if you recall, with the NMOS we had 4 variants. We could sense at the drain. When I say sense the difference between the desired current I0 and the actual current ID at the drain terminal and feedback to the gate, and that gave us this topology. To sense at the drain, you have to connect the current source I0 over there so that the difference I0 minus ID flows into the parasitic capacitor and changes the drain voltage. And to feedback to the gate, you have to complete the feedback through a positive incremental gain. That is, the gate voltage should increase if the drain voltage increases, and the simplest implementation of this is of course a short circuit, where we have this. Okay, and we have seen how to realize amplifiers with this. Okay, now if you look at the PMOS counterpart, everything will be the opposite. So let's say I call this VDD, that is the source of the transistor which is connected to a fixed voltage. And like I've said before, because we operate with positive supply voltages, I'll call this VDD, and the lower rail will be called ground. That will be the common reference node of the circuit. And we have to sense the difference at the drain node. This is ID and this is I0. So now the difference ID minus I0 flows into this parasitic capacitor. If the drain current is smaller than desired, then this current will be pulled out and the drain voltage tends to fall down. Okay. Also, if the drain current is smaller than desired, if ID is smaller than I0, the gate voltage VG must be decreased. Okay. This is because the source gate voltage VSG must be increased, right? So VG must be actually reduced. And how do I do that? If ID is smaller than I0, what happens is this voltage goes on decreasing. So the variation at the drain is exactly in the same direction as the variation we need at the gate. This is exactly the same as in the NMOS case. So again, just like before, we have to complete the feedback through a positive incremental gain. This means that VG increases if VD increases. That's the role of this positive incremental gain. And the easiest way to do that is by connecting the drain to the gate directly. Okay. In this case, you know that ID will be equal to I0 in steady state. Okay, in steady state meaning this voltage is not changing anymore. Okay, and if this is VDD, this VSG will be adjusted such that drain current ID equals I0. In other words, VSG will be equal to the threshold voltage plus square root of 2I0 by mu1 Cox W by L. Okay, exactly the same as what we had in case of the NMOS transistor. That will be the value of VSG. Okay. Now, will this transistor be in saturation? For it to be in saturation, VSD has to be greater than VSG minus VTP. So as long as VTP is positive, which is the most common case, then this will be in saturation. Okay. Now, because we have already discussed these things in detail with NMOS, I'll go a little quickly through the PMOS alternatives. The second one was to sense at the source terminal and feedback to the source terminal. What did we do in the NMOS case? Because we are feeding back to the source, the gate terminal was tied to some fixed voltage VG0 and the drain was not used, so it was connected to the upper rail VDD. To the source, we connected a current source I0. And it turned out that we didn't have to do anything more, because this connection here means that if ID is more than I0, okay, then current flows through this parasitic capacitor and the voltage increases. And also, if ID is more than I0, we have to reduce the value of VGS so that ID is restored to I0. To reduce the value of VGS, we have to increase the source voltage. But that's already happening simply because of this connection. And as I mentioned earlier, the source terminal is part of the controlling side and the control side of the MOS transistor. So, the feedback is implicit here. There is feedback. If there is a difference between ID and I0, the source voltage changes and that will change the drain current. Okay. Exactly the same thing with PMOS. In case of PMOS, the drain terminal is not used, at least as far as the operating point picture is concerned. So we connect it to ground and the gate is connected to some fixed voltage VG0. Usually it's obtained using a resistive divider, and to sense the difference between ID and I0, we connect the current source to the source terminal, and any difference I0 minus ID will flow through the parasitic capacitor. So if ID is smaller than I0, this means that a current gets pumped into the parasitic capacitor and the source voltage increases. Okay. Also, if ID is smaller than I0, we had to increase VSG. Again, you see that nothing more has to be done because the gate voltage is fixed, the source voltage is increasing. So that means that the moment you make this connection, if ID is smaller than I0, the source gate voltage VSG will increase, and finally steady state will be reached. That is, this voltage will stop moving when ID equals I0. Okay. So that's all that's there to it. So that is source feedback biasing, or sense at the source and feedback to the source. Source feedback bias with a PMOS transistor. Okay. And then using the usual procedures, we can turn this into any kind of amplifier. Okay, we have to have this picture for biasing arrangement, and the input source and the load must be connected to appropriate places for realizing an amplifier. Okay. The third alternative was to sense at the drain and feedback to the source. And to sense at the drain, because we are feeding back to the source, the gate is tied to a fixed potential VG0, and to sense at the drain, we connect the current source to the drain, and any difference I0 minus ID will flow into that parasitic capacitor. And here we know that if ID is too small, if ID is smaller than I0, then a current will go this way and the drain voltage will increase. On the other hand, if ID is smaller than I0, the source voltage must decrease so that the gate source voltage increases and the current becomes closer to I0. Okay. So the sense of variation we want at the source is opposite of what we have at the drain. So we have to complete the feedback through some stage which has an inverting gain, which has a negative incremental gain. Okay, and one of the possibilities is to use an op amp. Okay. With a PMOS transistor, again, the gate is tied to some fixed voltage VG0, and to sense the difference at the drain, this is ID and this is I0. The difference current ID minus I0 flows through the capacitor. If ID is greater than I0, then this voltage goes on increasing. Okay. Now, if ID is greater than I0, what must happen is that the source voltage must reduce so that VSG reduces. Okay. So the sense of variation we want at the source is opposite to what we have at the drain, exactly as in the NMOS case. So we need a negative incremental gain between the two. That is, if the drain voltage increases, the source voltage must reduce. Okay. And a possibility is to use an op amp. There are many things that you can use, but we can use an op amp. Here, and the gain has to be inverting from the drain to source. So we have minus plus, we connect it that way, and if I call this VD0, the voltage here will be VD0 in steady state, because the op amp, I am assuming it's an ideal op amp, it has a virtual short between its input terminals, so this will be at VD0. Okay, and the gate is at VG0. The source gate voltage has to be such that the transistor carries a current I0, which means that the source gate voltage has to be VTP plus square root of 2I0 by mu1 Cox W by L. Okay. So the voltage here would be the gate voltage plus the threshold voltage plus 2I0 by mu1 Cox W by L under the square root, and this part is known as the gate overdrive voltage. Okay, basically it is VGS minus VTN in case of an NMOS transistor, or VSG minus VTP in case of the PMOS transistor. It's basically the amount of excess voltage after turning on the MOS transistor that is present. Okay, to turn on the MOS transistor you need a threshold voltage, and beyond that you have this amount, and that's called the overdrive. Okay, and the last of the possibilities is to sense at the source and feed back to the gate. And again, because now the drain is not in the picture, we just connect it to the supply voltage VDD. To sense at the source, we connect a current source I0. Now we know that simply by connecting it to the source we have feedback at the source. Okay, in this case the feedback is not purely to the gate, there will be feedback to the source as well, but we can provide additional feedback to the gate by completing the feedback through a negative incremental gain. Okay, this is because the sense of variation you need at the gate is opposite to what you have at the source. So in this case also I write feedback to the gate, there is feedback both to source and the gate. But if this amplifier has a reasonably high gain, then there is substantial feedback to the gate and lot less feedback to the source. Okay, and how do we do this with PMOS? Same principle. The drain is not used in the operating point picture now. To sense at the source, we connect a current source to the source terminal, this is I0, this is ID, and I0 minus ID flows that way. So if ID is smaller than I0, Vs increases. Now if ID is smaller than I0, Vsg must increase. Therefore, Vs must increase or Vg must decrease, or both. Okay. In this case, Vs does increase, but we also want to have feedback to the gate, so Vg must decrease. So again, the sense of variation we need at the gate is opposite to what we have at the source. So we complete the feedback through an inverting stage or something that has a negative incremental gain. So this really means that the gate voltage reduces if the source voltage increases. Okay. And an example is to use an op-amp, again because we need an inverting structure. We do this, the inverting terminal of the op-amp is here. This is Vs0 in that if this is an ideal op-amp, because of virtual short when it's in negative feedback, this voltage will be at Vs0, and you can calculate the gate voltage. It will be Vs0 minus the threshold voltage plus the overdrive. Okay. That's the last of the variants for biasing a PMOS transistor at a given current. Now you can take any one of these biasing pictures and turn it into a common source amplifier or any other kind of amplifier that you wish to have. Okay. Now when you already have a working topology with NMOS transistor, you don't have to derive the PMOS topology from scratch. There is a systematic way of converting NMOS circuits into PMOS. That will be the subject of one of the following lessons. Okay.